Hello all, this is the Pencrest High School AP Physics C video series. This is video 1B, derivatives with respect to time. Now you may recall the progression that's shown below from position to velocity to acceleration. As we go down this progression, in our prior experience, we went down the progression using the slope of the graph. You'll notice that the formula is here. Velocity is the change in position over time. Acceleration is the change in velocity over time. We are going to add another term to this progression. Again, we're continuing down the same progression with respect to time. We're going to call the next term jerk. It's also called surge. Jerk is a change in acceleration over time. You can see how the units work. As we move down the progression, we go from meters to meters per second squared, meters per second cubed for the jerk term. The jerk term does not have a universal symbol, so we will use a lowercase j. Now, last year, graphically, we kind of did this the hard way, particularly finding the instantaneous velocity at a specific time. We constructed a tangent line, picked 2 points on the line, and found the slope. What we're going to look for now is a method that is a little more purely mathematical, has less variation in the answers, less subjectivity, doesn't depend on sort of eyeballing the tangent line and so on. So this is going to come from the calculus, and it's going to involve what we call the derivative. Okay? As we go down this progression, from position to velocity to acceleration to jerk, we're going to use what's called the derivative. Now, we're not going to address the theoretical considerations of the derivative. That's more of an issue for your math class, pre-calc or calculus. Since we're going to use the derivative as a tool, we're more interested in exactly how to get it and what it means. Put simply, the derivative of a function tells us what the slope of the function is at any point on the domain of the function. Most of our functions will have time as the independent variable, so it'll be a function of time. When we find the derivative will also be another function of time. It's possible that it can be a constant, but we'll see when that happens. Now, the general form, which is called the power rule, the general term for the derivative of any term in a polynomial function, y equals some constant a times t to the n, n is some exponent. We're going to call the derivative dy over dt. These d's here, these are not variables. Okay, they indicate very small deltas, very small changes. So you might recognize delta x over delta t as a velocity function. If this y were a position function, and we say that y equals a times t to the n, dy dt is a very small change in the function over a very small change in the time. And the way we find this functionally, we take the exponent n, move it out front. We have n times a, we carry the constant with it, times t to the n minus 1. So effectively, we decrease the exponent by 1, and this is the power rule. dy dt is the derivative of y with respect to time. Okay? Now, if you had a series of terms, you might see a polynomial. Y equals at to the n plus bt to the n minus 1 plus ct to the n minus 2. Each of those terms gets its own derivative. It gets differentiated independently. We have dy dt. Here is the first term's derivative. We take the n out front, times a times t to the n minus 1, plus we take this exponent n minus 1, move it out front, times b, carry the coefficient along with it, times t to the 1 less n minus 2, and then we move this n minus 2 out front, times c, t to the n minus 3. You can see how the progression works. Now, what we want to do is look at the generic position formula. You'll recognize a couple of elements here. The new issue here is the jerk term, the 1/6 jt cubed. We'll get into that in a little more detail later on. For now, what we want to do is take the derivative with respect to time. So we're going to say x is a function of t. We're going to take dx dt. So the derivative of x with respect to time. This x naught, you'll note, does not have a t in it. Therefore, it doesn't have a derivative term. So this constant term goes away. We start with v naught t. We take the exponent of t, which is 1, move it out front, times v naught t to the 1 minus 1, which we know is 0. We'll clean that up in a minute. We'll take this 2, move it out front, 2 times 1/2 times a naught t to the 2 minus 1, which is going to end up being just a t term, and then 3 out front times 1/6 jt to the 3 minus 1, which will be jt squared. So when we simplify, we get a generic term for the velocity of an object with respect to time. Again, dx dt is the change in position with respect to time. We define that as the velocity. If we take the derivative, we get a functional relationship for the velocity. In other words, this is the generic velocity with respect to time. It now has a jerk term in it. We're not familiar with that, but again, functionally the progression is pretty easy to follow. If we take another derivative with respect to time, we get dv dt. V again is a function of time, so we do the same operation. The v naught goes away. We have an exponent of 1 here. We move it out front. 1 times a naught times t to the 0. We know t to the 0 is 1. Plus, we take the 2 out front. 2 times 1/2 jt to the 2 minus 1. We'll end up with a pretty simple expression for the acceleration with respect to time. Again, it has a jerk term, but this implies that the acceleration is not constant. So that's the nature of the derivative. Okay, this is something that's called the power rule. You will learn it in pre-calc and calc. From a much more theoretical standpoint, we tend to use it in a more practical manner when we're given a generic position function and we need to find the velocity as a function of time, or we need to find the acceleration as a function of time. So the power rule is pretty easy. We'll get a little more complicated later on when we look at some sine and cosine functions, but for now the power rule will do. And next up is going up the progression, which is integration with respect to time. Until then, I'll see you soon and enjoy.